Alright friends, in this screencast we're going to take a look at how to build toward the derivative of a polynomial. That's the plan. We don't want to write limit h approaches 0 for the rest of our lives, so if there were some shortcuts that helped us out in finding derivatives of polynomials, we would be most grateful. And to get there, we've got to build there because we want to do so in a rigorous way. We want to prove each step along the way that what we're doing has merit. So we begin with the simple idea: the derivative with respect to x of a constant is 0. And this idea has some initial merit to it. If I graph a constant, beep, I've got my flat line. It appears that the slope of that line all the way is 0. And if I have a line and I draw a tangent line to the line, it appears to be the line itself, and the line has a slope of 0, so it appears that the derivative is 0. We can prove that without too much trouble. We take the limit as h approaches 0 of our function at x plus h minus our function at x, because they're the same no matter what your x value is, divided by h, and that, my friends, is in fact 0. So that's important. Whenever I ask you for the derivative of a constant, you're going to say 0. If I can, let's build. Let's pretend that I had some function u. U is a function of x. And I multiply it by a constant. I do a stretch in the vertical direction. Well, that is equal to that same constant times the derivative of u with respect to x. And that almost makes sense, because if I do a vertical stretch on a function, then I should do a vertical stretch on all of its tangent lines. And that turns out to be not too bad. If I want to prove it, I take the limit as h approaches 0 of our function at x plus h minus our function at x over h. And a little bit of algebra here in class. That's a u. Right? So what have I got? This c can come out to play, and what's left? The limit as h approaches 0 of this thing. Wait a minute. By definition, the limit as h approaches 0 of this thing is the derivative of u with respect to x. Oh, wow. Right. So, of course that makes sense. Things that make sense. If I have two functions, u and v, and I add the functions and then take the derivative, that's the same as taking the derivatives and adding them together. Again, an idea that makes sense. If I combine two functions by adding them, I should be combining slopes of tangent lines. This seems reasonable. Take the limit, h approaches 0, our function at x plus h minus our function at x over h. So let's rewrite this, and let's rewrite it in the following way. I can break this up into two fractions, where on the left I've got u of x plus h and then minus u of x, and on the right I've got v of x plus h minus v of x. And so this thing on the left is the derivative of u, and this thing on the right, limit as h approaches 0, the thing on the right is the derivative of v. And so, sure enough, if I add two functions and take the derivative, that's the same as adding the derivatives of the functions. Then there's the one that's not intuitive. The derivative of x to the n is n times x to the n minus 1. This is commonly referred to as the power rule. The derivative of x to the n is nx to the n minus 1. And you're thinking to yourself, well, maybe. Let's try to prove it. Take the limit as h approaches 0. Our function at x plus h minus our function at x over h. And then it boils down to how you factor the difference of two nth powers. And this is where the algebraic fun comes in. When you factor the difference of two nth powers, here's what you get. You get the difference between the bases, and then you get the first guy to the n minus 1, that should say minus 1, and then you get that to 1 power less times x, and then you get, so then what happens is that the powers on x plus h get smaller by 1 as we go across, and the powers on x get bigger as we go across until we get to x to the n minus 1. So what happens? Well, firstly, this is h and this is h, so they drop out. Secondly, we let h get small, and as we let h get small, this is basically x to the n minus 1. This is basically x to the n minus 2 times x to the 1. Wait, that's x to the n minus 1. And that's x to the n minus 1. And all of these become x to the n minus 1. So we get x to the n minus 1, but how many times? 1, 2, 3, n of them. And that's a nice proof that the derivative of x to the n is nx to the n minus 1. So why does that piece matter? Well, that piece matters because if I want to differentiate f of x equals x cubed minus 3x squared plus 5, then I know from all the rules that we've just talked about, the derivative of x cubed, well, the 3 comes down in front and the power decreases by 1. And then I'm just subtracting a couple of functions here, so I just subtract their derivatives, and then this is a stretch on that function. I know the derivative of this function is 2x to the 1, so I just multiply that by 3, that's a vertical stretch, and then I'm just adding some functions together, so I add their derivatives together, and we learned that the derivative of 5 is 0, because the derivative of every constant is 0. And so we end up with 3x squared minus 6x. We can take derivatives of polynomials very easily just by using the power rule over and over and over again. In the next screencast, I'll show a few more examples of derivatives of polynomials and how they might apply to things that don't look like they're polynomials, but, well, they're close enough. Okay, thanks.